Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is actually meant for those who are possibly in a pre-calculus course. Even though this is in my trigonometry series, it's because of the fact that often this specific topic is held off for a little bit until you've kind of mastered trigonometry, because you get all the core concepts down in trig, and then the little additional stuff that you'll need for the higher level mathematics gets kind of draped over later on. And this is one of those. We're going to condense the expressions of the form a sine of x plus b cosine of x into a single expression. This is going to be very valuable in signal processing and differential equations, which might be several courses away, honestly, but it's a good skill to use or to have. And so we're going to go ahead and develop that skill now. The material you need as a prerequisite is the sum, or I should say the sum and difference formulas for the sine and the cosine, but really specifically the sine formula. And actually, I'm going to go ahead and remind you of those right here. So let me read the example first. Let's invent a way to condense the expression a times sine of x plus b times cosine of x into a single trigonometric function. Now, if you look at that expression, it's very, very close to the sum of angles identity for the sine curve. So what I mean by that is the following. Recall, the sum of angles formula for the sine is the sine of x plus phi, and I'm specifically using this notation because we're going to have a theorem that uses the same exact notation. So x and phi are just angles, in radians likely, but it could be in degrees. Anyway, sine of x plus phi is sine of x times cosine of phi plus sine of phi cosine of x. Now, why did I choose to use different colors for the angle phi and the trig functions of the angle phi? Well, it's because if you look at what we're trying to transform here, which is the a sine of x plus b cosine of x, really that a and that b, if I wrote those in green, a and b, you could see that this matches up very closely to the sine of x plus some angle phi. If we can rewrite or compress a and b into trig functions, then we might be able to write that expression as a single trig function sine of x plus some weird angle phi. And sorry about my screen, my Wi-Fi is terrible. If we take this expression, let me go ahead and write it out here. A sine of x plus b cosine of x, and we decide to multiply each of those terms by the number 1, but a very special form of the number 1. I'm going to go ahead and mention it here. Maybe I'll just go ahead and do it. So I've multiplied the entire expression just by the number 1. But the number 1 that I've chosen, the form of the number 1 that I've chosen, is the square root of a squared plus b squared. Now, obviously, that is reminiscent of the Pythagorean theorem and the hypotenuse of the triangle used for the Pythagorean theorem. But there's a huge and very important reason why we do this. It's called normalizing. So if I take this denominator and distribute it into each of these terms here, but I'll leave that square root of a squared plus b squared on the outside as far as the numerator square root. I'll go ahead and write this out. You get the square root of a squared plus b squared times the quantity a over the square root of a squared plus b squared times the sine of x plus b over the square root of a squared plus b squared times the cosine of x. And you may be thinking, well, why in the world would you do that? Well, the reason why is because if you can imagine, we have just created a triangle. I don't know what quadrant it is in, but that will just depend on A and B, but at least I could draw out a triangle to showcase it to you here. So let me draw this triangle out. And what we're going to do is just have the horizontal side, we'll just call that A, and the vertical side we'll call B, and then therefore, by the Pythagorean theorem, the hypotenuse is the square root of a squared plus b squared. Now, if I call this angle right here phi, which is why I chose to use phi as an angle up above, if I call that angle phi, then I think you'd have to agree the cosine of that angle would be a over the square root of a squared plus b squared. And the sine of that angle would be b over the square root of a squared plus b squared. And so therefore, this is equal to the square root of a squared plus b squared times the quantity, I will call this sine of x times cosine of phi plus sine of phi cosine of x. Oops, parenthesis got a little bit mashed up there. Times the cosine of x. There we go. And that we can compress down into a single statement. This is square root of a squared plus b squared times the sine of x plus phi. And that allows us to rewrite this sum of trig functions, sine and cosine, as a single sinusoidal function, which is great for signal processing. That's what we want to do. And often, by the way, we will go ahead and call this coefficient by the letter k or something like that. So it is totally fine to do that. And in fact, in our upcoming theorem, we're going to write that. But it is kind of important to note that the quadrant that our triangle is going to be in depends upon the SIGN signs, the plus or minus signs, of these coefficients. It's just important for you to remember the coefficient of the sine, let's get right here, is going to stand for the cosine of a different angle phi, and the coefficient of the cosine is going to be the sine of that angle phi. So we're going to keep that in mind as we move forward. And here's the theorem. It's the sums of sines and cosines theorem. If a and b are real numbers, then a times the sine of x plus b times the cosine of x is some constant times sine of x plus phi, where that constant is actually just the square root of a squared plus b squared. We, in fact, have just proven this theorem, so there's no need for me to write proof down below. And phi satisfies the fact that cosine of phi is a over the square root of a squared plus b squared, and sine of phi is b over square root of a squared plus b squared. Again, remember, the coefficient of the sine is going to be the cosine of phi, and the coefficient of the cosine is going to be related to the sine of phi. It's not really the how do I say that? The coefficient of the sine is not actually equal to the cosine of phi, it's related to. And the coefficient of the cosine is not equal to the sine of phi, it's related to. There's got to be an adjustment on those coefficients, specifically division by the square root of a squared plus b squared. That's called normalizing. So let's see this in action, because this is actually pretty simple to do once you get the hang of it. So let's go ahead and write this expression here in terms of the sine only. We have a negative root 3 sine of x plus 1 times the cosine of x. Remember, the coefficient of the sine will be related, but not equal to, but related to the cosine of phi. And the coefficient of the cosine, which is a 1, I could write that in there, I suppose, is related to, but not equal to the sine of phi. The good justification why the coefficients aren't equal to those trig functions is that the cosine of phi can never become a negative root 3. Negative root 3 is less than negative 1, and cosine can't be less than negative 1. So therefore, those coefficients would not, or at least that specific coefficient wouldn't work for a trig function like the sine or the cosine. Anyhow, how do you make it workable? Well, you go ahead and pretend as though those are sides of a triangle, and I'll just take that coefficient of the sine there, and I'll use, since it's a coefficient of the sine, I'm going to use it as the horizontal side of a triangle. Notice I'm writing a negative root 3, and the coefficient of the cosine will be the vertical side of the triangle. Notice that I'm writing the positive 1. Now, if you think about that, in truth, if you had a triangle on a Cartesian coordinate system where the horizontal side was negative, but the vertical side was positive, you would actually be drawing that in quadrant 2. So it might be better for you to think of it as, oh, it's a triangle in quadrant 2 where I have some angle phi, but this is this side right here, the horizontal side is negative root 3, and the vertical side is 1. This allows me to find that hypotenuse very easily, and then I could talk about what all of the trig functions are if I need to. So let's go ahead and use Pythagorean theorem here. That's going to be 1 plus 3, which is 4, square root of 4 is 2. So there we go. And by the way, hypotenuses are always positive, so you don't have to worry about that ever becoming negative. Now what I'm going to do is I'm going to take this expression here, and I'm going to multiply top and bottom, numerator and denominators, by this hypotenuse length. That's it. So I'm going to take that entire expression and say, oh, it's 2 times negative root 3 over 2 sine of x plus 1 over 2 cosine of x. And this, actually, I haven't really changed the expression. If you distribute this 2 that's in the coefficient here, if I distributed that through, you will see it cancels with the 2's in the denominator, and it gets us back to the original expression. So this is no different than the original expression, just how we've written it, right? And so now I could ask, well, what is that angle phi? And as I've mentioned many, many times, trig is about only really 2 things: quadrants and reference angles. We are in quadrant 2, and technically speaking, this is not phi. This is the reference angle for phi. The true angle for phi is this angle from standard position. So we want to know, what is that angle phi? Well, this is a special triangle, isn't it? 1, 2, root 3. Right? If I drew out a 1, 2, root 3 triangle, pi over 6, pi over 3, right angle 1, 2, root 3, you could easily see that phi hat there, the reference angle, must be pi over 6. That's our reference angle. And if our reference angle is pi over 6, the actual angle must be 5 pi over 6, because we're in quadrant 2 with a reference angle of pi over 6. Now I can go ahead and finish out this problem. I'll take my time with it, and I'll say it's 2 times the cosine of some angle phi. Let's just pretend that we haven't found it yet, sine of x, plus the sine of that same angle phi. Let's just pretend we haven't found it yet, times the cosine of x. And that is the sum of angles formula for the sine. So that's 2 times the sine of x plus phi. But we happen to know what phi is. It's 5 pi over 6. So I could just say that's 2 times the sine of x plus that 5 pi over 6 that we found, because again, we have a reference angle of pi over 6, and our actual angle is in quadrant 2, so our actual angle must be 5 pi over 6. Again, trig is all about reference angles and quadrants, and if you are in a pre-calculus course, you've had a full course of trig, so this, at least the background information of finding reference angles and quadrants, shouldn't be too terrible. It's a little bit confusing at first, but once you get used to it, this is actually kind of a fun process, not too terrible. Let's do another one just to really see how these examples work out in all situations. So again, we have some expression here. Write this in terms of only sine. Well, the first thing I'm going to do actually is just distribute that 12. Why? I don't know why. I just want to. So I'm going to take that 12 and I'm going to distribute it to both of those terms. So I have 12 sine of 3x, sine of 3x, minus 12 cosine of 3x. Remember, the coefficient of the sine is going to be related to the cosine of phi, and the coefficient of the cosine is going to be related to the sine of phi. It's not going to be the same, but it's going to be related. Well, what I'll go ahead and do is draw a triangle. Think about it this way. If that's related to the cosine of phi, then the cosine of phi must be positive because that's a positive number. And if this is related to the sine of phi, it's not equal to it, but if it's related to the sine of phi, then the sine of phi must be negative. Now, in which quadrant would we have cosine positive but sine negative? If you say quadrant 4, you are 100% correct. It is going to be a quadrant 4 angle. So there you go. I'll go ahead and draw a triangle that emanates into quadrant 4. Remember, the horizontal side of this triangle is going to be related to the cosine. So it's going to be of length 12, positive 12, because it's going in the positive x direction. And the coefficient of the cosine here is going to be related to the sine, which is the vertical side. So that's going to be a negative 12. There we go. And by the way, this is the angle phi. Now, you know, this is going to be a 45-degree angle because those two sides are of the same length. So our reference angle, I'm going to call it phi hat, because it technically is supposed to be a reference angle. Our reference angle is phi hat. And we know that from the Pythagorean theorem, this is going to be 12 root 2 in length. So I'm going to multiply both numerator and denominator by 12 root 2. I'll get this. Multiply top and bottom by 12 root 2. 12 root 2. And then if I multiply top and bottom of that expression by 12 root 2, I'm going to take it, this denominator, I'm going to distribute it in to each of those two terms so that you don't have to do two steps. So we have 12 sine of 3x, and that 12 is over 12 root 2, and minus 12 cosine of 3x, and again, that 12 is over 12 root 2. Again, all I did was take the denominator that was written here and I distributed it to each of those two terms. Little simplification, you get 12 root 2 times 1 over root 2 sine of 3x minus 1 over root 2 cosine of 3x. Having done that normalization, it reduces the coefficients of these trig functions from being of size 12 down to something of size less than 1, which is very important when you want to transition over to sines and cosines. And we happen to know our reference angle is going to be 45 degrees or pi over 4 radians, and we're in quadrant 4. You could write this in two ways. You could write it with a positive angle or a negative angle. I don't really care. If you write it with a positive angle, then your angle would be 7 pi over 4. If you write it with a negative angle, then your angle would be a negative pi over 4. It's the same solution, so it doesn't really matter to me what you do. I think I'm going to go with the negative solution just because I want to. Not because it's the right one, but just because I want to. So this is going to be 12 root 2 times, I'm just doing it slowly here, the cosine of phi, sine of 3x, minus the sine of phi, cosine of 3x. And that is the sum of angles formula for the sine. So it's 12 root 2 sine of 3x plus phi. Oops, that's sine of 3x minus phi. It's actually a little bit easier to see this if you write it in the proper order. So if I write this, use commutative law of multiplication and write this as sine of 3x cosine of phi, it's a little bit easier to see. that the order is 3x and then minus phi. And then you can let phi be either 7 pi over 4, or you could let phi be a negative pi over 4. Doesn't really matter. That's going to be the same thing. I'll just let it be a negative pi over 4. So 12 root 2 sine of 3x minus a negative means plus pi over 4. There we go. We have completely transitioned that expression involving two trig functions into a single expression involving only one trig function. And now we could talk about the period of that function, which is 2 pi over 3. We could talk about the phase shift, which is a negative pi over 12. We could talk about its amplitude, which is 12 root 2. These are things that you would not be able to talk about with a sum or a difference of sines and cosines. You just can't do that very easily, that is. So this is why this is an important skill as you move forward, especially in engineering, in audio engineering.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.